In this tutorial, we will do some shelf life calculations for a quality attribute that follows zero order reaction. Let's look at this example. We have a fruit juice that is stored, and there is a browning occurring in that juice during storage. The product is stored for 60 days, and we measure the optical density to determine the browning. That is measured at 10-day intervals. So first we want to determine if the browning reaction can be characterized by pseudo zero order kinetics. And second, we want to calculate the shelf life if the optical density of 0.24 signifies the end of shelf life. We will do this problem using a spreadsheet where we will first enter the data for optical density measured at 10-day intervals. So here we have the experimental data on optical density from 0 to 60 days entered in the various cells of the spreadsheet. So the first thing we will do is highlight the experimental data, which is in cells A2 through B8, and then we will insert a scatter diagram, and we will observe that the experimental data now is plotted on the scatter diagram, and we will right click on any of the points, and then from the dialog box we will select Add Trend Line. Now the trend line options that we will select are linear, and also we will select Display Equation on Chart and Display R-squared value on chart. So now we have the line plotted for the experimental data, and the equation along with the R-square is also shown in the graph. Note that the R-square value is 0.9996. Since the data fit has a very high R-square value, we observe that this indeed is a zero order reaction since we plotted the optical density versus time. Now from the equation of this line, note that the slope value is 0.002. So we can enter that here in the spreadsheet. That slope is 0.002. Now we'll go back to our original screen, and we note that from the spreadsheet we obtained a slope of 0.002 units of optical density per day, and that gives us the rate constant, the zero order rate constant, as 0.002. Note from the tutorial for zero order reactions that the shelf life is given as AE minus A0 divided by K. Now AE is the concentration of the attribute. It could be concentration or let's say in our case optical density at the end of shelf life, and that in the problem is stated as 0.24 minus A0, where the A0 value was the initial optical density, which was 0.05. This was from the experimental data that was provided to us, divided by the rate constant that we just obtained as 0.002. This gives us the value of 95 days for the shelf life. Note also that if we look at the units, they cancel out for the optical density value units, and we are left with days as the units for the answer. So that means it will take 95 days of storage for this fruit juice to become unacceptable when its optical density will reach a value of 0.24.